Yeah, today we're going to talk about SplitFT, the fault tolerance for disaggregated data centers via remote memory logging. The basic idea of the paper is, well, hey, we have a cloud, we need to store stuff in the cloud. What kind of storage systems we have? This paper looks at traditionally kind of single node storage systems like RocksDB or SQLite or something like this, right? And these systems would work in a very kind of simple way, right? So you will have a box, and that may be your RocksDB, right? And then it will sit on top of some file system, and it will talk to this file system, right? So anything that needs to be written disk, it will be written to file system, right? On that single node. Now, the paper claims that since we live in an age of cloud, this file system can be replaced by something fancy, right? So instead of a single file system, like a file system on a single machine, we can have some kind of disaggregated or distributed file system, right? So now, if we have these distributed file systems, it's no longer just one machine. It's no longer immediately on your computer. It will probably be like located somewhere over the network, and it will have multiple copies for your data, and it will also have like multiple copies for the metadata, right? So if we put our RocksDB or SQLite on top of these distributed file systems, we can achieve fault tolerance, right? So even if the machine crashes, we can bring up the RocksDB or SQLite or whatnot on another machine and just connect it to the distributed fault tolerant file system that we already have. Right, so that's kind of the basic motivation for this paper, right? So they look at this particular kind of setup, right? And what they find, once they run RocksDB in this setup, what they find is that it's like painfully slow, right? And they argue that it is slow because we have two things that needs to happen, right? So RocksDB will write logs, right? So some like write ahead log or whatnot. So every operation, every update, it will be logged, right? And then eventually, when the log reaches certain size, right, we need to write this into an SS table. So RocksDB is like LSM3 backed system, right? So SS table, right? And there are a few things that they note, right? So logs, they tend to have small writes. And SS tables, they tend to have big writes. And they claim, after the experimental experimental confirmation of this, that it's this small writes that kill the performance, right? Because you append something to a log file, maybe few hundred bytes, but you need to reach the distributed file system. It needs to replicate this data. It needs to update metadata. So a lot of things happen like behind the scenes in that distributed file system, right? In this disaggregated storage. So they say that we're doing a lot of these writes and all of them are slow, right? We want them to be f-synced, we want them to be durable so that we don't lose data, and that synchrony across all of this like underlying components of distributed file system, which in their case they use Ceph, it is slow. So the argument that the authors of this paper make is, well, why not remove the slow file system for these small writes. So instead of having the logs and SSTs, all of these things go to distributed file system, why not only have the big items go to the distributed file system, and small items like logs and whatnot be replicated in memory, for like very quick access, right? So essentially, the big stuff goes to file system. The small stuff, the stuff that we need, just like for durability of the system, the logs in particular, goes and replicates in memory. So there is no actual like physical copy on disk, on drives for these logs. They'll just replicate it in memory. And they will do it in a transparent manner for the RocksDB, more or less, right? So with like minimal modifications to RocksDB or SQLite or like other single node systems that they try. And essentially, what the way they achieve this is they have a shim layer that sits here, right? And they call this NCL, Near Compute Log Library, right? And this shim layer kind of sits in between the the application and the file system. And if you need to, let's say, write to a log, you will open that log file with a special flag that will designate that file as NCL file. And what this library does, it kind of keeps track of like, okay, you have this NCL file open, so it's not going to go to distributed file system. It's going to go to completely separate system for handling those, NCL for this like small writes files. And yeah, so what is this system? Right. So they have some kind of a controller, which is a zookeeper, so it's replicated. And they say that they want to use memory of like other compute nodes, because the authors claim that the memory is like largely not utilized well in data centers. So there is plenty of like unused memory that they can borrow. So the machines, the compute machines, can register themselves with Zookeeper and provide some memory, like a disaggregated memory pool. And whenever RocksDB starts up and opens up that NCL file, it will go talk to Zookeeper, and it will get 3 peers, 3 other machines that are willing to share their memory, and it will use these 3 machines, right? Out of however many are registered with Zookeeper, to actually perform like in-memory writes using one-sided RDMA, right? So the NCL library is going to maintain a copy, in-memory copy of that file that the top layer RocksDB or SQLite is writing, and then it will also use RDMA to replicate all these updates, appends, and whatnot to 3 copies somewhere in your data center, right? And as soon as it hears from at least the majority, it considers this operation durable, f-synced, right? And then it returns back to RocksDB, making RocksDB believe that it's actually like f-synced to a file system, whereas in fact it just sits in like multiple locations in memory in your data center, right? And obviously, it's all RDMA, it's low latency, and it's quick, right? And the NCL library kind of is mapped to like this particular set of machines, and also manages like what happens when the machines may go like offline, like replacement and whatnot. Right. So the recovery story is very simple. Like if RocksDB, if that guy fails, you just start a new one and you go to Zookeeper, you learn who were the backups, the in-memory backups for all of the NCL files that were used by the crushed machine. And then you go and fetch those logs from those in-memory copies. So yeah, that's kind of pretty much it for like the big picture, right? So the paper goes into a little bit more details on how they reach anything here, right? And they let all the big files like SS tables that are being flushed to storage go to the normal distributed file system. But for all the smaller like writes, which they claim are the logs in those storage systems, RuxDB, SQLite, Redis, they go to the in-memory and they actually never persisted to disk. They just store it in 3 copies plus a copy that you have in memory, like locally here, right? So 4 copies in total. And yeah, so that's what this paper talks about. Let me scroll to the evaluation really quickly. They've done some evaluation. They run some like YC interest or like workload A, right? Because that's a 50-50 read-write workload. And the purple line is strongly consistent, meaning like fsync is being done after every write version backed by the distributed storage system. So here we have the throughput. And the brown line, I believe, the picture doesn't really have the legend, but I believe, the colors match. So the brown bar is the SplitFT, split fault tolerance. So they achieve the performance kind of on par with not strongly consistent version that doesn't do fsync after every update, right? And that's largely because all of these small things that you need to fsync to disk, they actually went through like more complicated. So workloads C, they are read-only workloads, right? So they don't get as much benefit. Interestingly, they don't have the workload E, which has the scan operations. But yeah, and the paper doesn't really describe what these workloads are. I had to like go and refresh my memory by reading by CSB like manual on like what these workloads try to do. And yeah, I think I will stop with my short presentation at this point.